Hello everyone, welcome to the lecture series on VLSI and microelectronics. It is a subject in 7th semester, BTech ECE, the course code is EC702. I am Paulu Sridhar, course coordinator, assistant professor, Department of ECE, Guru Nanak Institute of Technology. So let us start today's lecture. So today we are in lecture number 7 of the lecture series in VLSI and microelectronics. The course code is EC702. So our subject contains 45 number of total lectures and the credit is 4. The total contact hours are 3 lectures plus 1 tutorial per week, which makes it as a 4 credit subject. So we are in module 1, that is Introduction to ICs. So in Introduction to ICs, we will be studying about the ICs, advantages, disadvantages, limitations, scale of the integration, SSI, VLSI, LSI, ULSI, then Moore's law, scaling of the MOSFET, constant field scaling and constant voltage scaling, short channel effects, VLSI design flow, Y chart, IC classifications, standard IC and ASIC, PAL, PLA and the FPGA architecture. Next are the course outcomes. So there are 6 course outcomes of this subject, and the course outcomes are very important because they play a very important role as the students will able to analyze him or her according to the course outcomes, because the course outcomes will be fulfilled once the course is completed. And in this slide we will be saying which course outcome will be completed after this particular lecture number 7. Okay, now let us see the course outcomes. The first course outcome is able to describe scale of the integration, SSI, MSI, LSI, VLSI, Moore's law, scaling, short channel effect, VLSI design flow and architecture and contact gate level circuit with PLA and the PAL concept. Next is able to analyze CMOS inverter voltage transfer characteristics with the parameters VIL, VIH, VOL, VOH, VTH, and based on the knowledge of digital circuit design methodologies like CMOS, pass transistor, TG, DC-VSL, dynamic logic, NODA, and able to construct schematic of the combinational sequential circuit SRAM, DRAM cell using MOSFET. Now, based on the fundamental concept of the MOSFET characteristics and model, this is the third course objective, able to calculate value of the resistance of the current source, MOS diode, current of the current mirror circuit, voltage of references like the voltage divider, threshold voltage and band gap, emulate resistance of switch capacitor circuit, gain of switch capacitor integrator and first order switch capacitor filter. The fourth course outcome is with the help of the MOS transistor model able to calculate the value of the parameters to design CMOS differential amplifier and two-stage op-amp. The fifth one is able to describe fabrication steps of the IC and construct stick diagram and layout of the CMOS inverter and basic gates based on the lambda and micron design rules. 6 is able to calculate gate delay, dynamic power, short circuit power and leakage power, and total power consumption across CMOS inverter circuit based on the derived expression of the delay and power. So these were the 6 course outcomes, and among these 6 course outcomes, the first course outcome, that is able to describe scale of the integration, SSI, MSI, VLSI, Moore's law, scaling, short channel effect, VLSI design flow and architecture, and contact gate level circuit with PLA and the PAL concept. This course outcome will be fulfilled after the completion of this particular lecture, that is lecture number 7. So let us move to the next slide. The next slide brings us the lesson plan of this particular lecture. Lecture number 7, the course name is VLSI and Microelectronics, and the course code is EC702. So we are in module number 1, Introduction to ICs, and we will be studying today IC classification, VLSI design styles, field programmable gate arrays, FPGA, that is a short form of field programmable gate arrays, and also the programmable logic devices, that includes the PAL and the PLA. So let us start the lecture number 7. Now before starting lecture number 7, let us have a quick recap of the previous lectures. So the first lecture started with explaining the syllabus and also why we will be studying the VLSI subject. Next, we have seen the ICs overview, that is the advantages and the disadvantages of the ICs. Next, we have studied about the scale of the integration, that is the SSI, MSI, LSI and VLSI. Next, we have studied about a very important law in the VLSI subject, that is the Moore's law, which indicates that the number of transistors on chip is increasing on an exponential rate. Next, we have studied about the scaling of the MOSFET, which included the constant field scaling and the constant voltage scaling. After the scaling, we have studied the VLSI design flow and also Y chart, which is an important part in the VLSI design flow. Next, due to scaling, we have the effects that are occurring in a MOSFET. We have studied such effects like the small geometry effects. The small geometry effects are of two types, such as the short channel effects and the narrow channel effects. In the short channel effects, we have studied about the channel modulation or the channel length modulation, threshold voltage lowering, punch through, sub-threshold conduction, velocity saturation. After all these, we have studied about narrow channel effects and the other small geometry effects. So let us start the lecture number 7. So the starting of this lecture, let us have a quick review of the ICs, the integrated circuits, or the ICs, also called the micro electronic circuit or the microchip or the chip. Integrated circuits are an assembly of the electronic components fabricated as a single unit, in which miniatured active devices such as the transistors and the diodes and passive devices such as the capacitors and resistors are there. Integrated circuit ICs interconnections are built up on a thin substrate of semiconductor material, typically silicon. The resulting circuit is thus a small monolithic chip which can be as small as a square centimeters or only a few square millimeters. The individual circuit components are generally microscopic in size. Now you can see this diagram that it is a typical IC, a small IC that is being shown in a fingernail. You can guess how small it can be from this diagram also. Now let us move to the next slide. Now we will see the major disadvantages of the ICs. The major disadvantages of ICs over those made by interconnecting discrete components are as follows. In an IC, the various components are part of a small semiconductor chip and the individual components or components can be removed or replaced. Therefore, if any component in an IC fails, the whole IC has to be replaced by a new one. Limited power rating, as it is not possible to manufacture high power. Example, suppose 10-watt ICs. Need of connecting inductors and transformers exterior to the semiconductor chip, as it is not possible to fabricate inductor and transformers on the semiconductor chip surface. Operation at low voltage, as ICs function at fairly low voltages. Now let us move to the next slide. Now the disadvantages are continued. quite delicate in handling as this cannot withstand rough handling or excessive heat. Need of connecting capacitor exterior to the semiconductor chip as it is neither convenient for economic to fabricate capacitors exceeding 30 picofarad. Therefore, for higher values of the capacitance, discrete components exterior to IC chips are being connected. High-grade PNP assembly is not possible. Low temperature coefficient is difficult to be achieved. Large values of the resistance of the transistors are there. Next is voltage dependence of the resistance and the capacitance. And the next one is the diffusion processes and other related procedures used in the fabrication process are not good enough to permit a precise control in the parameter values for the circuit elements. However, control of the ratios is at sufficiently acceptable level. So these are the disadvantages of the ICs. Now let us move to the next slide. That is the types of the ICs, which are very important. Now let us see the types. Depending on the types of the substrate devices, signal processing and applications, ICs are classified into various types. So this is the diagram which shows the classification of the ICs or the integrated circuits. The material used for ICs can be either silicon, gallium arsenide, that is GaAs, or silicon germanium. The table shows the classification of the ICs on the basis of the types of substrates. Now, based on the substrates, this is the classification, that is silicon, gallium arsenide, then silicon germanium. Based on the type of the devices, these are the types of ICs: bipolar, CMOS, BiCMOS, MESFET, HBT, and HEMT. Next is based on the type of the signals such as the analog, digital, mixed, and the radio frequency RF. First one is the digital ICs. These ICs are operated only with digital signals. Next is the analog ICs. These ICs are operated with only analog signals. Mixed signal ICs. These ICs are operated with both analog and digital signals. RF ICs. These ICs are operated with radio frequency signals. Now, based on the applications, standard part TTL or TTL equivalent ICs at SSI, MSI, and LSI levels. These are general purpose ICs, example microprocessor, memory, etc. Next is application specific standard products, that is the ASSP. The examples include a controller chip for PC, a chip for modem or modem, etc. Next is the application specific integrated circuit, that is the ASIC. In short form, it is called ASIC, or we also called it as ASIC. Examples are a chip for mobile phone, for satellite, a chip for toy, etc. Now let us move to the next slide. That is, based on the devices used for implementing the ICs, they are classified as follows. That is, this part we are going to explain: bipolar, CMOS, BiCMOS, MESFET, HBT, and HEMT. Okay. Now let us see one by one. Bipolar. In these ICs, bipolar junction transistors, BJTs, are used to implement the ICs. Next is the CMOS. In the CMOS ICs, combination of the NMOS and the PMOS transistor are used to implement the ICs. Next is the BiCMOS. In these ICs, combination of the BJTs and the CMOS transistors are used. Next comes the MESFET. Metal oxide field effect transistors are used in these ICs. Next is the HBTs. These ICs are used or uses heterojunction bipolar transistors. Next is the HEMT. High electron mobility transistors are used in these ICs. So these were the types of the integrated circuits, and so you have seen that these ICs are based on different types of applications, such as based on applications, based on the type of signals, based on the types of the devices, and based on the types of the substrates. Now let us move to the next slide. That is the VLSI design styles. This is also very important because we are going to study the FPGA, then the PLD devices from this design styles only. So let us start. Depending on the applications, cost of productions, performance, and the volume of the production, there are different VLSI style design styles that are followed to implement a chip. Each of these styles has its own advantages and disadvantages and is chosen on the basis of the target application. The commonly used design styles are as follows. Field programmable gate array, that is the FPGA design. Second one is the gate array design. Third one is the standard cell based design. Fourth one is the full custom design. Fifth one is the semi custom design. And sixth one is the programmable logic devices, that is the PLDs. Now we will be discussing the FPGAs and the PLDs because these are there in your syllabus. So let us discuss about the FPGA, that is the field programmable gate arrays. Now, field programmable gate arrays or FPGA is a fully fabricated chip or fully fabricated IC chip in which the interconnections can be programmed to implement different functions. Now, an FPGA chip has thousands of logic gates which can be connected to implement any logic function. This is a typical FPGA architecture. You can see that there are IO blocks, there is a horizontal routing is there, that is you can also say as the interconnects. Then the configurable logic blocks are there, and again there is a vertical routing channel, that is vertical is this one and horizontal is this one. Okay, so there are three types of components here. Okay, just look at this one. These are the logic blocks, this shaded ones are the logic blocks. This one is the vertical routing channel routing or the routing of the channel. This one are the IO blocks, input output blocks. This whole ones are the input output blocks, this blocks, and this one is the horizontal routing channel. I hope this diagram is clear to all of you. Now let us move forward. Now this FPGA or the field programmable gate array, it has the following three components. First one is the input output buffers. Second one is the array of the configurable logic blocks, that is the CLBs. And third one is the programmable interconnects. Now let us again move to the next slide. Now in the FPGA based design, first a behavioral netlist is written to describe the functionality of the design. This is done using the hardware description languages such as the Verilog and the VHDL. This Verilog and VHDL, we will be studying all this in the VLSI practical classes. We will also be doing the practicals, and VHDL is a language there. We will be learning this language in that platform. Okay. Next is then the net list is synthesized to come up with the gate level design. The next step is to map the logic blocks into available logic cells. This process is called technology mapping. This is followed by placement and routing, which configures the CLBs and defines the interconnections. The next step is to generate the bit stream and download the bit stream into the FPGA chip with the help of a software interface. Then the FPGA chip can function as a desired as long as the power is on, or it can be reprogrammed. The benefits of using FPGA based design are that the design cycle time is very short and very much suitable for low volume prototype development with low cost. A concept can be quickly implemented in the hardware and checked if it is worth implementing in large volume. But FPGA based design is not optimized for performance. The typical design time is few hours to couple of days for a FPGA based design. Okay, these are the disadvantages you can say, and these are the advantages. So you can see that FPGA is having many advantages. Now let us move to the programmable logic devices. So the programmable logic devices, PLDs, are standard products which can be programmed to obtain the desired functionality required for a specific application. The programming can be done either by the end user or by the manufacturer. So normally the programming or the programs are being done by the end user or by the manufacturer. So this is a very important point in the programmable logic devices. The PLDs which are programmed by the manufacturer are known as the mass programmable logic devices, or it is also known as MPLDs. The PLDs which are programmed by the end user are called field programmable logic devices, that is the FPLDs. The architecture of the PLDs is very regular and fixed. It cannot be changed by the end user. The PLDs have wide range of applications and have low risk and low cost in manufacturing in large volume. Hence, the PLDs are cheaper, as the PLDs are pre-manufactured, tested and placed in inventory in advance. The design cycling time is very short. The PLDs are classified in three categories based on the architecture and programmability. First one is the read-only memory, that is the ROM. Second one is the programmable array logic, that is the PAL. And third one is the programmable logic array, that is the PLA. In your syllabus, you are having PAL and the PLA, that is the programmable array logic and the programmable logic array. These two are very important and they may come as the short notes and also in the 5 marks questions. So let us see what is PAL. Now PAL is the programmable array logic, is another programmable architecture which can be programmed to implement the desired function. The PAL architecture is shown in this figure. This one is the programmable AND array and this is the fixed OR arrays. So here M input lines are going and these are the outputs. These outputs are going as the inputs to the fixed OR array and we are getting the N output lines. Okay, this is the block diagram of a PAL architecture, that is the AND followed by OR. So it is a programmable AND gate or plane followed by fixed OR array of planes. That's why it is known as the programmable array logic. Okay. Now let us see. PAL also includes flip-flops so that it can be used to design state machines. The AND array is programmed to generate the product terms or literals to the Boolean functions to be implemented and then ORed by the OR plane to generate the functions. I hope this PAL or programmable array logic is clear to all of you. Now let us move forward to the programmable logic arrays, that is the PLAs. In contrast to the PAL, programmable array logic PLA has both programmable AND array and OR array. The AND array is programmed to generate the product terms and then ORed by the programming OR array. This one is the programmable AND array. Here you can see that M input lines are going and these are the outputs, and from here we are getting the N output lines. The structure is given here. This is the block diagram of a PLA architecture. Now, what are the comparisons in case of cell size, cell type, cell placement, or the interconnections? There are various comparisons in the full custom cell, then standard cell based gate array FPG and the PLDs. Okay. But in your syllabus, the PLA, PLD and the FPGAs are very important. Please try to read them minutely because they will be surely coming in the exam. Okay. Thank you all of you for listening to me and also hope to meet you soon. Thank you again.